Now, so far in this class, we've focused on the derivative. And practical examples for this in business, of course, it's always that you have a cost or revenue or profit function, and you want to find the marginal cost or the marginal revenue, the marginal profit. So we take the derivative. Well, what if we knew what our marginal profit was, and we wanted to find what our profit function was? Well, this process would be going the opposite way, and it's called antidifferentiation or antidifferentiation. Now, as you might guess, we're given some kind of function, and we're given the first derivative of it, and we want to find the original function. In taking the derivative, we've had an original function and we found the derivative. Now we're going the other way. We have the derivative, we want to find the original function. So that's what antidifferentiation is referred to. It's the process of finding the original function if we're given the f prime of the function. So the example here, a very simple one. If the first derivative is 2x, and then we know that the original function is going to be x squared. And we can check that by taking the derivative of the original function, and we would get the first derivative. So one of the nice things about this section is that when you do it, you can rather quickly then, once you find the antiderivative, you can take the derivative of it just to make sure you did your work right. Maybe even get 100 on the exam. We'll see. Now, mathematically, we don't necessarily say, oh, here, you're given the first derivative. We just have some function, and that's what they refer to here as f of x. It's a function. And the antiderivative, they refer to as capital F of x. So we know that it's related. And concept-wise, this would be the first derivative of this function. And that's what this line means, that if we take the derivative of capital F of x, we get the function that we started with. So concept-wise, we are given the first derivative. We want to find the original function, but we don't look at it that way in practicality, or in theory, I should say, because we're simply given a function, and we don't know anything else about that. We just want to find what its antiderivative would be. And of course, the capital F of x, the original function in my example, is considered the antiderivative of f of x. Now, hopefully this isn't too hard. It's just, if we think of taking the derivative as going from the original function down to the derivative, well, concept-wise, then we're going from the derivative up to the original one. So the concept hopefully is not too difficult. Now, if we look at this function, f of x equals 9x to the 8th power, we want to find all antiderivatives of this function. Well, if we think about how we take the derivative, we could kind of reverse that process to find the antiderivative, right? So one way of thinking of this would be, well, if we had x to the 9th, and we wanted to take the derivative of that, we know it's going to be 9 times 8x to the 8th power. And realistically, since we're going up, we know that here, when we're looking at x to some power, when we take the derivative, it always goes down by 1. So to do the antiderivative, we always want to make it go up by 1. And we multiplied things together. The exponent, any coefficient was there. If this is going up to the 9th power in the original function, which is there, well, then if we went from here down, we'd say this is going to be 9x to the 8th. Well, that's where this 9 came from, basically. We know that that comes from the exponent of the antiderivative, so we get this answer. Now, that's concept-wise what's happening. We have a formula for it that makes it easier to not have to rely on logic, we'll get to very shortly. Therefore, we would say that x to the 9th is an antiderivative of 9x to the 8th. We say that because, well, it's only one of them. There could be several of these. Whenever we took the derivative of a function that had a constant in it, like x to the 9th plus 5, we'd simply said, well, the derivative of any constant is 0, so it just drops out. Well, so then if x to the 9th is one of the antiderivatives, x to the 9th plus 5 is another possible one. X to the 9th minus 17 over 2 would be another possible one. So we realize there's actually a lot of antiderivatives Because we don't have any information about the constant that's there, we'd have to say that we want to look at all possible constants. Well, we do that by simply saying that the antiderivative is going to be x to the 9th plus c, where c is any constant, any particular number. So when we're doing this, it actually becomes important to remember this when doing the antiderivative, that when we're done, once we calculate what it is, we always put plus c to acknowledge that there is some number there, some constant, and we don't know what it is. Now, there are ways to find this if you're given enough information, and we'll go over that shortly. But for now, just remember that any antiderivative will always be in the form of whatever you find the antiderivative to be plus c. Now, we have some new notation to learn, and it's this. Suppose that f of x is a function whose antiderivatives are capital F of x plus c. The standard way to write this is this. Well, here, this looks like it's an elongated s. Well, it kind of is. This is the integral sign. It means you're going to take the integral of this f of x function, which means you want to find the higher function of this, and it's going to equal this capital F of x plus c, plus the constant we just talked about. Now, there's a new thing in here also that says dx. Well, that looks familiar. What does that mean? Well, for right now, we're going to think of it as simply saying we're doing the integral of f of x with respect to x. As in, all of our answers are going to be in x's. Our answer is going to be in x's. F of x is going to be in x's. And when we do that, we're going to get capital F of x plus c. Now, as I indicated earlier, that at some point, again, we're going to see that this dx also has an algebraic value, and we're going to use that today. If you remember, we took the derivative using the Leibniz notation. We had said if we had dy over dx, that was the derivative of y with respect to x, but it also had an algebraic value. Well, this is the same thing. Here's the dx part of that. It also has an algebraic value, and we'll get into one possible application of this. But for now, just think of it as all of our things have to be in terms of x. So the entire notation, the integral of f of x dx, is called the indefinite integral. That basically means you don't know which area of the integral you're looking for. We're taking the integral, we're doing it for the entire function. We could be looking at it from x is equal to 1 to x is equal to 5. We could be looking at the integral from 1 to 1,000, or from negative 5,000 to minus 5. Well, the indefinite part of it means we're looking at any part of it, which means, in reality, that we're looking at the integral of the entire function from negative infinity to positive infinity. And it's a formula, or a function, and that hopefully makes some kind of sense. The indefinite integral means we're not limiting it to any values of x. It's all possible values of x. Now, later in a future lesson, we'll go over the definite integral, when we are looking at it from x is equal to 1 up to x is equal to 5. But for now, we're just looking at the entire function. Now, to take the integral, there are several rules that are helpful that make this very easy, instead of trying to process it through and figure it out logically. Now, while it looks a little bit scary because we're not used to this integral sign yet, it's not actually very difficult once we get used to it. This integral, again, means we're going to take the integral of x to the r power. The dx means, again, with respect to x. And when we do that, there's a formula that we can use. That's 1 over r plus 1, where again, r is the exponent that goes with the x, the power. So we add 1 to r, 1 over r plus 1 times x to the r plus 1. Hopefully, this part of it makes sense. We're going to take r and increase it by 1 since we're going up. And, of course, remember to tack on, at least at the answer, plus c. If you don't want to write it every time in your work, at least make sure it's there for the answer, because it needs to be complete. Technically, in math, it should be on every step. But, again, we're business majors, so let's just work through it. And at the very end, make sure we have the plus c there to acknowledge that the constant is unknown at this point. The only other thing I would mention is that this works when taking the integrals of simple integrals when for any r values except when r is equal to -1. It's a special case. In business, we don't really hit that too much, so I'm not going to bother teaching it. It's possible that you will, and may have to pick that up on the side, but it's not hard to do, but I don't think it's worth teaching it in a business calculus course at this point, at least. So the homework, I've avoided all the problems when r is equal to -1. I won't put it on any quiz or exam, so no worries about it. Just think about using this one. And oftentimes refer to this as the simple integration, because we're doing basically simpler functions. Now, if you're relatively good at math and you were paying attention here, you said, well, 1 times this is going to be this, the r, x to the r plus 1, and then you would end up dividing it by r plus 1. By that I mean, the formula could be done this way, and this is the way that it's taught in many different places. This is also the way it's taught in many different places. They're the same formula. If we took 1 over r plus 1 and multiplied by x to the r plus 1, 1 times x to the r plus 1, it's going to be x to the r plus 1, and we still need to divide it by r plus 1. So you could use whichever of these you want to use. Both formulas are correct, and they are actually the same thing. The book uses this top one, the 1 over r plus 1, so I will also use that in my examples, but you may use either one for your homework and for the exams. It means the same thing. Now there are also two other functions, or two other rules of integration, I should say, that we're going to look at today. The one is, the first one we just did, and the second one is, well, what if you had a constant in front of the function? What do? And what if you had two functions that you're adding together? What do you do? Well, that's what these are. But first, let's go back to the first one with this integral of x to the r dx equals 1 over r plus 1, x to the r plus 1 plus c. If we wanted to do this, if we have some function f of x equals x to the 5th, what we would do is to work with this. Now, we want to take the integral of this function. So that's going to be the integral of f of x. So we would write that as the integral of x to the 5th dx, putting it into the format that we see above here. And that equals 1 over r, where our r, in this case, is 5. So it's 5 plus 1, x to the 5 plus 1, x to the 5 plus 1 plus c. So it's relatively simple to do. Now from here, of course, what we need to do is to finish the simple math, and this becomes 1/6 x to the 6 plus c. So it's not hard to use, it's just a matter of becoming familiar with it and, of course, memorizing it as you do the homework. It's a simple process. Now, if we had 1 over x squared, in this case, well, put it this way, if we were taking the derivative, we know we would have to convert this to x to the minus 2, right? Well, the same kind of setup. It has to be in the same format for taking the integral, so we need to convert this to x to the minus 2. Now we want to take the integral of x to the minus 2, and our r is now minus 2. So it becomes 1 over minus 2 plus 1 times x to the minus 2 plus 1. And of course, remember the negatives there, they are part of the exponent. So that's going to be 1 over minus 1, which is minus 1, which we don't have to write the 1, of course, but we need the negative x, times x to the minus 2 plus 1 is minus 1. So we get that. Not too hard. It's just maybe a half a step harder because of the negative. To remember to apply the negative. Now when we're doing the square root, we end up, again, in the same situation. We need to convert it to x to the 1/2. Now when we take the integral of x to the 1/2, our r is 1/2, so we can use fractions with this. This would become 1 over 1/2 plus 1. Well, that's 1/2, or 3 over 2. And this will be the same thing, x to the 3 over 2. Now, we can't leave it in this form because it's 1 over 1/2. So what we can do, surprisingly, if this, we can just simply flip this over. That's the surprising part of it, and say that it's 2/3. Why is that the case? Well, we remember from our high school algebra, or high school math actually, that if we have a fraction divided by a fraction, we invert the denominator and multiply. So we could take 1 and change it into 1/1 divided by 3/2. Well, that's going to be 1/1 times, we flip this over, 2/3. Well, 1/1 times 2/3 is going to be 2/3. So that is true. That's actually based off of a math principle that if you have 1 over a fraction, what you can do, the answer will be simply invert the fraction over. So some students like to show the in-between work of showing the 1/1 times 2/3 to get to 2/3. But because of this law and the fact that we understand this, and I'm teaching it this way, that this will be true. So you can just go from here, take the denominator, the bottom fraction here, and flip it over to become 2/3. And you can just do that without any explanation. I'll know that you know what you're doing. Now, this rule of integration works when we have a constant in front of the function. And for example, when we do this, the function f of x is equal to minus 5x cubed. The k is simply the constant that's in front of the x value. So the k is minus 5. And if we're going to take the integral of minus 5x squared, the integral of some number times the function dx is equal to that constant times the integral. So we would simply write it as minus 5 times the integral. Whenever you have just any number in here, whether it's minus 5 or 5,000 or minus 3/2 or 1.006, you can simply move that number outside of the integrand. Think of it as the value of this is going to be multiplied by 5. The same thing happens here. You take the integral of this and then multiplied by minus 5. The same thing happens here. It's similar to how we took the derivative. It becomes part of it. We need to multiply it by what's in front of it when we're done taking the derivative. The same is true with the integral. We can move it outside. We're going to multiply it by minus 5 after we take the integral of this. So now the integral of this, we again use this particular formula that we just learned. And our r is 2. So that becomes minus 5 times 1 over 2 plus 1, x to the 2 plus 1. Now as we look at this, whereas, well, this is just the minus 5 times all of this. Well, couldn't we just jump straight from here to this step if we wanted? Yeah, that's combining the two formulas together. The integral of a function, or a constant times a function, is the constant times the integral. Well, and the integral of that is this, so why can't we just do k times this? And that's what this is saying. So yeah, this becomes a little bit of a shortcut if you just want to jump straight to here. And in fact, if you want, you can use this formula all of the time instead of the other two. Just realize that if there's no k, there's no number in front of the x, well, then k would be 1. And you're just simply going to ignore the 1 because it's 1 times whatever it is. So this becomes one law that can replace these two. But concept-wise, we actually are doing the first one and then doing this one. And when we put them together, it's this third one. So now, from here, we're just going to simply, to finish the problem, do the simple math with this. This becomes minus 5 times 1/3 x cubed. And we, of course, that's going to be minus 5/3 x cubed plus c. Again, remember the plus c at the end. Now, this last one, it says that the integral of one function plus another function is equal to the integral of the first function plus the integral of the second function. And this is a lot like taking the derivative. This would be the first function, this would be the second function, and this would be the third function. So we can simply take the integral of each one. Written out, it's going to be the integral of minus 5x squared dx plus the integral of 14/3 x dx plus the integral of minus 3 dx. Now, I'm not going to require that you do each step like this, but some students find it helpful to write it out just to keep everything straight. When we're doing this, we already know from the prior problem, we just calculated the integral of minus 5x squared dx, and that was minus 5/3 x cubed. Now, the integral of this is going to be 14/3 times 1 over, well, here the r, the exponent is 1. It's not written, it's assumed to be 1. So it's 1 plus 1, and this will end up being x squared, of course. And then we're going to do the integral here. Now when I do this, it's minus 3 times the integral of, oh, well, what would that be? Here we use the 0 as r. Where did the 0 come from? Well, when we're doing this, the in-between steps that I didn't directly show there are the integral of minus 3 dx is the same thing as the integral of minus 3 times x to the 0. Anything to the 0 power is 1. So this is 1 times minus 3, which is minus 3. So the exponent, when you have just a constant with no x's, the exponent is going to be 0 because there's actually an x to the 0 that's not written there. So using the 0, our r becomes 0, so it becomes 1 over 0 plus 1 times x to the 0 plus 1. And continuing on with this, this is going to be what, 1 over 2. 14 divided by 2 is 7, so 7/3 x squared. And this one becomes minus 3x. And then, of course, the plus c at the end of the last one. You don't have to write plus c after each one because the constant is for the entire function, not for each of these separate terms. So again, when you get to the final answer, just make sure that there's a plus c here. The other thing I would point out is here we're doing the integral of minus 3, and there was no x there. And we get the same thing here, minus 3, but just an x afterwards. That's kind of a shortcut. And I tell students that it's understood. Everyone who's taking calculus can look at this and say, well, I don't really need to do the in-between step. Here, I know I should, but I'm just going from the integral of minus 3. I'm just taking that and adding an x on it. The integral of minus 3 becomes minus 3x. Sure, you can do that. It is understood. Everyone knows who's taking calculus knows that's what you're doing, and it saves the step of writing out something that's obvious, at least as far as calculus is concerned. So if you want to take that shortcut, please feel free. It's the same thing as when we were taking the derivative. If we were taking the derivative of minus 3x, we know the x would just drop off and we have minus 3. So we're just doing the opposite of that. We're going from the minus 3 to the minus 3x. Now, what is the effect of this constant that we've been working with? Well, we always add this plus c at the end. And we say, well, it's some constant, and so far we haven't defined what it is. But what effect does that have on the antiderivative? Well, here's two functions. Let's suppose that these were the antiderivatives of a function that we were given, and we calculated it to be this. Now, when the blue line is 1/4 x cubed minus 3, and it's this line. And if we had the red line, it's the same function, but we're adding 5 to it. Well, that's simply going to push the red function up to where, the blue function up to where the red function is. Well, the slope of this, again, when we have the antiderivative, if we take the derivative of the antiderivative, we get the derivative. And the derivative is the slope. If we look at the slope here, it's going to be the same as it is here. When x is equal to 2, the slope is going to be 0. The slope is going to be 0. At x is equal to 3, the slope looks like it's maybe somewhere between 2 and 3. And the same here when x is equal to 3. It's, again, the same angle. So all it does is take our answer and push it up or down. So if we were doing this, taking the antiderivative of a function, we would usually say it's 1/4 x to the third minus 3x plus c out here. Well, if that c is 5, it's simply going to push it up here. That's the only effect that this has on this. Everything else is going to be the same. The derivative would be the same thing. Will be the same at all the points. So if we have an idea where the antiderivative, if we have a point where this goes through or have some way of identifying the location of this line, then we could actually find what C is. And that's what we're going to do here. Here, we want to find the antiderivative. We want to find the function f of x for which the first derivative is equal to x squared minus 2. And we know that if we put 1 into the antiderivative, we'll get a value of 4/3. Now, if we take the antiderivative of x squared minus 2, we're going to find our antiderivative to be 1/3 x to the third minus 2x plus c. Again, c is the constant. Now, if we were to graph several different choices for this graph, they would look something like this. This 1/3 x to the third minus 2x is what all of these are, and we're just doing a c of different values. Here, c is equal to 0, so it's this line. When c is equal to 1, it's this line. When c is equal to 2, it's this line. When c is equal to minus 4, it's this bottom line. So the graph is going to go through somewhere here. Well, do we know where this graph is going, where our antiderivative is actually going to go through? Yes, we do, from this statement up here. If we did an f of 1, we get 4/3. Well, that's a point, isn't it? If we find the antiderivative, which we did, and put 1 in for x, we're going to get an answer of 4/3. So our x is this and our y is this. It's the point 1 and 4/3. Now we can use that. Well, since we know it goes through this point, we could come down here and say, oh, okay, at 1, it goes through the point 4/3. No, that's less than 1. This next one, oh, that looks like that could be 4/3. It's a little more than 1, but it's less than 2. We follow this over. Oh, the c is going to be 3. Well, but it's a little hard to tell. I mean, what if it was 2.9 instead of 3, or 3.08? Well, there's a more exact way to do that, and that is if we know that our antiderivative is this, and we realize that an f of 1 equals 4/3, we can calculate what c is. If we take our function and do an f of 1, it will equal 4/3. So let's do an f of 1. It's going to be 1/3 x, well, x cubed, x is 1, so it's 1 cubed, minus 2 times x, 2 times 1, plus c. And we know that this is going to equal 4/3 because an f of 1 equals 4/3. So now we have all numbers and c, so we can find out what c is. We simply calculate that it's 1/3 minus 2 plus c equals 4/3. So we calculate that c is equal to 3. So we can say, yes, it definitely is this equation when c is equal to 3 that we're looking for, this one here. So this becomes a simple way to do it. If you know a point on the antiderivative, even though you don't know the formula or what the function is, if you know the first derivative, you can find what the function is. And if you know that it goes through a point, you can calculate what c is. Now when we're done, we always state what the actual antiderivative is. We now know that c is equal to 3, so we need to replace the c with the 3 to say that it's this specific function out of all the possible ones. So the final step, to get full credit on an exam or quiz, for example, you want to calculate what c is and then rewrite the whole equation stating what it is. That seems a little picky, but math is interested in those kind of details. Now, working with a business function, here is a business problem. A company's marginal cost is this function. C prime of x is equal to this. That means, again, the marginal cost means they're working with the derivative. And it's in litres, where x is the number of units produced in one day. How many units we make every day. The company has fixed cost of 1,000 litres per day. Find the cost of producing x units per day. Okay, well, how much is it going to cost? Well, again, if we want to find the cost function, we're given the marginal cost, we need to take the antiderivative. So we're going to find the marginal cost by calculating the antiderivative of c prime. And if we do that, the integral of the cost of the marginal cost function is going to be, again, you can use your formulas, but it's going to work out to be this. remember to plus C. Now, we actually want to find the cost, and we know what the fixed costs are. Well, then don't we have a point on the antiderivative, on the cost function? Remember from an earlier lesson what fixed costs are? Well, our fixed costs are the cost that we have before we've produced anything for that day. The cost of rent, electricity, that kind of thing. Well, that means that we haven't produced anything yet. And even if everybody reports in sick and nothing gets built that day, no one works, it's still going to cost 1,000 liters for that day. So we know that if nothing is produced, that's going to be a C of 0. And the X would be 0, and the Y is going to be 1,000. That's going to be the cost. So if that's the case, we realize there's probably a shortcut, but first, to explain the long way, we do a C of 0 equals 1,000. So kind of have it reversed here. 1,000 equals a C of 0, and a C of 0 is this. Well, this is going to be something times 0, which is 0, minus 0, plus 0, plus C. So obviously the C must be 1,000. So we kind of knew that before, right? Now to rewrite out the answer, the cost function is going to be this. There's 0.005 x cubed minus x squared plus 80x plus 1,000. So whenever we're working with a formula like this and our fixed costs, we know, well, that's when no work is done. So we can do a C of 0, or we can just simply realize the shortcut that no work is done. There's going to be a cost of 1,000 liters. So that's going to take this antiderivative and push it up 1,000, because that's simply how much cost there is. The rest of this cost is going to be for what it is that we are producing, whatever it may be. So the shortcut is just to find the antiderivative and tack on, say, plus the fixed cost for the day. And we can say that that's a business application. We're business majors. We understand that, so we don't really need to explain it. And that would be fine on an exam. I won't ask you to explain it. If you still want to calculate it, you can. It's okay, because it is technically correct, and it is how we actually calculate it. So the applications for most of this function, most of these sections where we work with antidifferentiation, the practical application is that you're going to have the marginal cost, the margins, either the marginal cost, marginal revenue, marginal profit, and you want to find what the cost is, what the revenue is, what the profit is. So the business applications are not too difficult. Anytime you're working with antidifferentiation, anytime you see this funny integral sign, you know you want to take the derivative and go up higher, the antiderivative, and try to calculate what C is if you're asked to do that. Now, another application then with this would be, suppose that you currently produce 30 units. The current production level is X is equal to 30. Determine the amount cost will rise if you raise production to 60 units per day. So when the production level is raised to X is equal to 60 units. Well, we started with the first derivative, the marginal cost, and we calculated the cost function. Well, we could just do a C of 60, right? To find out what the cost is when we do 60 units, and a C of 30 to find out what our current production level is. Well, then we subtract the two. Take the higher and subtract the lower one. Putting it in terms of math, if we want to find the difference between these two, determine the amount that cost will rise, we need to subtract the two. Finding the total cost is for 60 units is the C of 60, and the total cost of 30 units is a C of 30. To find the difference between the two, we have to take the larger and subtract the smaller. So C of 60 minus 30. So when we're doing this, we calculate a C of 60, use the answer that we got, this 0.005, and then it's going to be 60 to the third power. And when we put it into our new equation, which includes this plus 1,000, the answer will be 3,280. Do a C of 30, and the answer will be 2635. Now we're going to subtract the two to say that the increased cost is going to be 645. And again, the problem said we were working in liters, so the marginal cost is in liters, so will the cost function be in liters. So remember to tack that onto the end. So this becomes a quick way to find out increased cost. If you're going to increase production, how much more is it going to cost you? So problems like this will be in the homework, and this is the homework. Again, you can see this on Moodle. You can get this on Moodle. And have a good day. We'll see you in class.